My PC was running out of storage space, so I decided to build a DIY file storage server, or NAS. In this video, I will tell you how the file server part of this project went. I did try to use the system for stream encoding as well, but gave up on it in the end. I will talk about that in the next video though. First, let's talk about why I chose to build a file storage server. The options were cloud storage, adding disks to my rig, buying a NAS, or building a file server. Cloud storage cost will quickly add up if you have a lot of data to store, and it is slower than the other options. Adding disks to my rig is the fastest and cheapest option, but I wanted redundancy, and there was not enough space for that in my rig. Buying a NAS would give me redundancy, but it would be more expensive than building one from computer parts I already had lying around. And in case the NAS would break, I'd have to get another one from the same brand or restore the RAID pool from backups. Anyway, let's look at the hardware next. I'm using my old Intel i7-930 CPU and Gigabyte GAX58 UD3R motherboard. I only have 6 GB of triple channel DDR3 memory. I'd rather use ECC memory and more of it, but that wasn't an option for now. The GPU is a GTX 1050 Ti, which is only borrowed, so I'll have to replace that at some point. The power supply is a cheap 650 watt Sharkoon unit, and the case is an Intertech 4U4088S. The operating system is installed on a 2.5-inch 250 GB mechanical disk for now, and I have a 32 GB SSD for caching. The boot disk is a bit slow, but I don't mind that. For the data, I use 6 1 TB mechanical drives. 5 of them are 3.5-inch drives, and one is a 2.5-inch. It's suboptimal, but it is what it is. I also have a Blu-ray reader and DVD burner combo, just in case I want to play some PlayStation 1 or 2 games, or watch an old movie I have on DVD. Okay, let's get started with the build. The plan is to build the system without the storage disks first, and install the operating system. Then set up SSH so I can log into the file server without having to connect a keyboard, mouse or even a screen. The next step is to add all the storage drives and set up a ZFS pool. I'm using a RAID Z2 setup to get the double redundancy and only lose 2 out of the 6 TB capacity. Installing Samba is up next. Lastly, I only have to test everything and copy all my files over. Building the system doesn't take very long, especially since the cable mass from the data drives is still missing. The CPU and RAM were still installed from a previous build, so I just have to wipe off the rest of the old thermal paste, install the CPU cooler and throw everything into a case. Installing the specific CPU cooler is always a struggle though. That one is not really in there. With the way it is designed, it is hard to line everything up properly. But it is the only one I have that fits in this case, and I didn't feel like spending another 10 to 15% of the project cost just for a new CPU cooler. I hate this cooler. It's blocked again. What? Oh. I hate this freaking cooler. It's impossible to install. Get in there. Come on. Oh, it's still not in. What? Now that everything is installed, let's start the system for the first time. It booted up just fine right away, so time to install the OS. Using ZFS means my choices are limited to FreeNAS, Vanilla FreeBSD or Ubuntu. I would probably be able to use ZFS on other Linux distributions as well, but I'm most familiar with Debian and its derivatives, and ZFS is supported on Ubuntu. I'm sure FreeNAS is amazing, but I wanted to learn a bit about SSH and Samba as well, so I decided to go with Ubuntu Server at first. While installing it, I decided to experiment a bit and try to encode live streams on the file server as well. This was a stupid idea. and I eventually went back to Ubuntu Server. The experiment is not part of this video, but I did learn some interesting things, so I will talk about that in part 2. Anyway, let's continue at the point where Ubuntu Server is installed and running. I should mention though that I assigned a fixed IP address to the MAC address of the file server. I did this within the settings of my internet router switch modem thingy, so I don't have to redo it in case I reinstall the OS. Let's install SSH next, so I don't have to keep my second mouse and keyboard connected. First, we need to install OpenSSH server and try to log in from the other machine. My file server won't face the internet, so just a password would be fine. But let's try to use a crypto key. We just need to generate an RSA key pair on the main machine, copy the public key to the server by running SSH copy ID locally on the main PC, and then deactivate password authentication. Next, let's change the config file so that it is not possible to SSH into the machine using the root user. Lastly, we need to restart the SSH service. Everything still works fine, so the SSH setup is done. Now that SSH is up and running, it's time to install the storage disks. This Intertech case comes with a disk cage, which can fit 7 3.5-inch drives. I removed the cage while building the system, and before we put it back into the case, we should throw the disks in there first. Plugging in all the power and SATA cables is the most annoying task of the building process, because there's not much space. Luckily, all the disks are recognized in BIOS, so no need to do it again, for now at least. So let's move on to the ZFS setup. First, we need to install ZFS utils and write down what the drives are called in the system. Next, we can create the RAID Z2 pool. Before we do that, we need to choose the name for the server though. Let's call it Red Spotted Purple. So the pool name is RSP0. The pool will be mounted to /RSP0. 2 of the disks already have a file system installed, so we need to remove those first. I like GNOME disks, so I used that real quick to delete the partitions that were still there. Now we can actually create a pool. There we go. Wait a minute, what is this chaos? Let's just redo that real quick. As far as I can see, everything is working fine now, so it's time for Samba. Let's create a few folders inside /RSP0, so I can easily set different access restrictions for each folder in case I need that in the future. Next, we need to set local user permissions to allow read, write and execute for all of /RSP0. Then we have to install Samba, open the config file and set up the Samba share and permissions for each folder. At this point, the Samba daemon needs to be restarted. It is also important to allow Samba through the firewall and to set a Samba password for myself. On the client side, using Samba is very simple. In Pop!OS, I just have to open the file manager, click on other locations, and enter the server's fixed IP address on the bottom. On Windows 10, I have to turn on network discovery and network sharing, and it automatically finds it. I just have to make sure the workgroup name in the Samba file on the server matches the workgroup name that is set in Windows. This is a relatively low budget project, so we should talk about cost. In total, I spent €297.68. I already had the CPU, motherboard, RAM, power supply, the SSD and the boot disk, as well as 2 of the 6 1TB data disks. €149.86 of the total cost was spent on the hard disks that I didn't have yet. The case plus various smaller bits and pieces cost €147.82 in total. For comparison, the cheapest 4-bay NAS that I found was around €220 without any disks included, and the cheapest 6-bay I found was €470 without disks. So I definitely saved a bunch of money compared to that. Now that everything is set up, let's test the server by transferring some files over. Transferring files works, but it's quite slow. The maximum write speed during the first test was only 85 megabytes per second. There are 6 disks in this RAID Z2 pool, so I was expecting to saturate the Gigabit LAN at 125 megabytes per second. I mean, the data is split into pieces and written to 4 disks simultaneously, so 125 megabytes per second should be possible, even with the 2.5-inch drive in the mix. Of course, the parity data has to be calculated, but I checked and the CPU is not the bottleneck. ZFS is only allowed to use 3 GB of RAM though, and it does use all of it. Also, up to this point, I still thought ZFS would use swap area for caching. So the SSD is set up as swap, and it is completely unused. I should fix that. Up until this moment, I was still experimenting with stream encoding, but then I gave up on that. I wanted to start all over, so I wiped the disks, reinstalled everything, remade the ZFS pool, and added the SSD as a caching device this time. The swap partition was replaced by a swap file. ZFS is now also allowed to use 5 of the 6 GB of RAM that are available. Time for another test. The speed did not improve, and this time the pool degraded during the transfer. Remaking the pool didn't help, and both times the degradation was caused by the same disk. I guess we should test the hard disks. It might also be a good idea to test new disks as soon as I get them. I was looking for a way to test hard disks and found BHT, a tool which lets you run multiple instances of BADBLOCKS at once. In order to run this script, we first need to remove the pool. BADBLOCKS completely fills up the hard disk and then checks if everything is read back correctly afterwards. It does that with 4 different patterns of 1s and 0s, so all the data gets wiped in the process anyway. I didn't delete anything from my other PC yet, so it's not an issue. Of course, writing and then reading 1 TB of data 4 times in a row takes a while, almost a full day actually. I don't want to bother connecting a keyboard, mouse and monitor, so I need to find a way to disconnect and reconnect through SSH without stopping BADBLOCKS. Luckily, there is the screen command. I basically connect to the server through SSH and then create a new session called HDD test. I then start BHT tool inside that session. Now I can just disconnect and reconnect later on, as long as I don't end the screen session. After running BHT for hours, the broken disk was found. In fact, BADBLOCKS found over 30 million errors while reading back the data it wrote in the first pass. And it showed me the serial number of the broken disk as well, so now identifying it was easy. I then attached that disk to a different SATA cable and port and ran BADBLOCKS on the broken disk again, just to make sure the disk was actually the issue. I knew this cable and port combination was fine because another disk got through all 4 passes of BADBLOCKS without a single error, while attached to this port and using this cable. At this point, I have to send the broken disk back to get a replacement. At this point, the file server setup is basically complete. I just need to replace the broken hard disk, then everything should run fine. However, I actually don't like the way the disks are mounted in this chassis. It is a 4U case, and the disks can fit in there when in upright position. That way, the case can actually fit 2 120mm fans to cool the disks, rather than just one. It would also be nice if the drive cage wasn't such a tight fit, because then I could at least fit a thin sheet of damping material in between the cage and the disks. I think the lower writing speed could have something to do with the vibration. So when I get the new disk, I will try to install the disks in upright position with some vibration damping. I will end this video here, since I'll have to wait for a replacement disk at this point. In part 2, I will talk about the experiments I did, trying to use the machine for stream encoding as well. It didn't really make sense because the hardware is not good enough to do both, but in essence it is possible to use a second PC for stream encoding without connecting a keyboard, mouse or monitor to it. So that's what I'll show in part 2. You'll also get a more clear picture of the timeline and everything that went wrong during this project. In part 3, I will try to install the hard disks in upright position and at the same time replace the 3.5-inch drive cage with something that reduces vibration. So stay tuned for that. Anyway, thank you all for watching and see you next time.